Hello, my name is Carlos Alberto Lopez Montalegre. My YouTube channel is Bit, and today I'm going over a case study in collision detection with the LBR iiwa Kuka robot. What is an LBR iiwa Kuka robot? It's a 7-axis robot designed by the German company Kuka, which is a world leader in automation. This is Kuka's lightweight cobot, a computer-controlled robotic device that is specialized for highly delicate assembly work and human-robot collaboration. Now, this human-robot collaboration can be as simple as doing engravings, helping humans pick up lightweight items, helping humans solder car parts, helping humans engrave the image of their desire in their car. There are lots of use cases for this Kuka lightweight robot. Now, the case study that take into consideration here is working for Pybullet Robotics Incorporated. In this video, I assume I will launch a Kuka robot for a company called Pybullet Robotics Incorporated. Suppose the CEO of Pybullet Robotics Incorporated, Richard Lesjester, assigned to me the task of training a camera to detect in real time whether an LBR iiwa Kuka robot collides with one or more obstacles. So it's a cube, a ball, table, and the floor, which also happens to be the plane of the Pybullet simulation that I'm going to work on. Now, the main idea for collision detection, this collision detection system is to perform binary collision classification. So the idea is to determine whether it's actually going to be a collision or a collision-free space, okay? What I'm going to use is a transfer learning scheme, which is a scheme in which the pre-learned weights of a convolutional neural network, more specifically ResNet 18, are used for a related task. So the learned weights are learned from an original data set and original task, and this learned weights are going to be used for a new data set and a new related task. Now, this task is just image classification. ResNet 18 originally classifies thousands of images, and now it simply has to classify 2 images. So it's a really simple transfer learning scheme. Now, there are 3 main advantages to using ConvNets, specifically ResNet 18. I'll say the first one is the inductive biases. So it's the translational invariance, meaning that a translated image of an LBR iiwa Kuka robot is still an image of an LBR iiwa Kuka robot, or an image of a collision translated, it's still an image of a collision, or an image of a bird translated is still an image of a bird, regardless of how it is translated. Additionally, the second advantage that I take into consideration is that convolutional neural networks take into consideration all components of the image. It takes into consideration the length, the width, the channels, sometimes even the opacity. And it goes from the most primitive features in its initial layers to more high-level features like whether it is a person or not. So it's like going from a simple line in the initial layers, which is a primitive feature, going to a high-level feature like the shirt, I don't know, the background that is behind me. And that's what the image classification does in this performing convolutional neural networks. And the last but not least advantage, which is the third advantage, is that I save a lot of resources. I save a lot of computing power. I save a lot of time, money that I would spend on servers, on acquiring data that is from the same distribution, because your validation data has to be the same for your test data. However, I'm going to use a small amount of data points, just 3,200 data points for training and validation. And that is what I'm going to take into consideration today. And surprisingly, I actually reach decent levels of accuracy and validation, and I'll show you later. So those will be the 3 main advantages. Convolutional neural networks are a real innovation in this field, especially for Pybullet simulations. Now, the tools I loaded are the Matplotlib, PyPlot, NumPy, OS, PIL, Pybullet, Shuttle, Torch, and TQDM. Now, I have 5 bodies in the simulation. It's going to be the plane, the robot, the cube, the sphere, and the table. The IDs are going to go for 0 for the plane, ID 1 for the robot, ID 2 for the cube, ID 3 for the sphere, and ID 4 for the table, okay? Now, the stage one is identifying collision positions and collision-free positions. I have a function that is collision long. I use it initially for examples of collision-free and collision spaces. However, in reality, I just use isCollision and the move end effector function. Now, for collisions, I'm going to use the getContactPoints function. This function returns an array of 14 objects. I'm going to just use 3 for isCollision, and I'm going to use essentially 4 for isCollision long, because I take, in the simple case, I only take into consideration the unique IDA and the unique IDB and the contact distance, which is negative if there is penetration. However, in the long version, I take the unique IDA, the unique IDB, the link index A and the link index B, and the contact distance. Moving on to stage one, identifying collision positions and collision-free positions. I will use the calculate inverse kinematics function, which takes as input the robot ID, the number of joints, and the target position in 3D space. The function focuses mainly on moving the end effector, which is the 7th joint, and it moves it to the desired position in 3D space, okay? Now here's a collision-free position. You can see that I move the end effector towards 2 in the C axis, right? It moves 2 above, and that's how it is initially, so that's why it looks upward. Now moving on, we have collision positions in which the robot is touching only the box. You can see it's touching ID2, there's only ID2. Then here's the robot touching the box on the plane. We have ID2, ID0. Now we move on to collision positions, taking into consideration the table. You can see it's ID4 only. Here's ID4 only in the case on the right. And here in the left, we have ID0 and ID4. It's touching both the table and the plane. Now here we have collision positions for the sphere. Here at the left, it's touching on the sphere. And now here on the right, it's touching both the sphere and the plane, okay? Now the stage 2 is data collection. When I take into consideration data collection, what I do is simply use the image index, the collision status. So image index is just its number in image production. Like the first image is going to have index 0, and the last image is going to have index 3199. That's going to be the index, the index, basic the index king. Okay. Now the collision status that we're going to take into consideration is just 0 and 1, 1 for collision, 0 for collision-free space. I'm going to use the mpl img.imsave, and I'm saving it to a folder called robot images. You see the format is a little bit different. You can put an underscore before the image index, or you can put an underscore only between image index and collision status just to separate them adequately. I prefer the later. And moving on to stage 2, you have to take into consideration the joint limits. We have 7 joints. Here are the limits. And what I'm going to do is multiply them by 2 later on when I collect the data. You can check here the documentation for the Kuka joints and their limits. So it seems like I didn't take into consideration the actual limits, but here, what I do is I subtract 1/2 from them and then multiply them by 2 to avoid any issue with it going above the pre-established joint limits. In future cases, I'll use a more specialized function for all joints. However, this one is more simple and it works efficiently. Now we move on to stage 3, dataset class. So the robot collision dataset objects are initialized with the root directory and desired indices arguments. So it's the root dir and desired indices are the original parameters. They use to form image in labeled tuples. Additionally, we need to change the image shape to 3, 512, 512. Originally, the image is 512 by 512 by 3, where 3 is basically representing the color channels, RGB, red, green, blue. And what I use is the permute function. And additionally, the images are appended to the image list and labels are appended to a label list. And only desired indices are taken into consideration. As you can see here in the function, when the index is not in desired indices, the function continues and basically accesses the index didn't exist. However, I only use this to divide the indexes into training and validation sets, okay? And you'll see on how I actually divide them. The stage 4 is load data. So you see that I only go up to the established index -1, and I go from that index to the num images. So for instance, I'm using 3,200 images. Okay, 3,200 images, 2,880, otherwise 90% are going to be used. So I go from 0 to 2,879. And then I go from 2,880 to 3,199 for the validation set, okay? Now, I also load the ResNet 18 model with its ResNet 18 weights, and I use a model variable in here. There's something you have to take into consideration when you work with this ResNet model. Like, you have to recall that the output layer for a neural network is the probability distribution over categories. Natively, ResNet has 100 dimensions in the output layer because it has trained for 1,000 category classification task. I loaded the ResNet 18 model with default weights into a variable called model and changed its dimensionality as necessary, okay? So here you can see that I changed its dimensionality to 2. It went from 1,000 to 2. That's a pretty big shrink. So you have to take into consideration that this 2 that I have in here really makes a difference. That is the only fine-tuning that I do. It's not that much. Like, it's even embarrassing to call it fine-tuning, but it is a little bit of what you actually need to go from 1,000 output layers to only 2, because you need a probability distribution over 2 categories, not 1,000. Now, in stage 5, the training model, there will only be gradient descent for training phases, as you can see, with torch set grad enabled, phase is equal to train. So only training phases will actually have gradient descent. I'm using stochastic gradient descent. Additionally, the criterion for loss is binary cross entropy loss, and the scheduler is a learning rate scheduler, the LR scheduler. Moving on, here are the codes for plots and visualization. So plot losses simply plot the validation and training losses as a function of epoch numbers. IMShow simply transposes the image matrix and multiplies it by the standard deviation and adds the mean to it. And visualize model shows the image prediction label collision or free and the actual label collision or free. So essentially what I do is just add that mean to bring it back to its original state. And then I undo the permutation of 3 by 512 by 512 and turn it into 512 by 512 by 3 image once again, so that I don't have an issue when I present it. Now, stage 5, train the model with 50 epochs. That my hyperparameters were 50 epochs, a learning rate of 0.01, 0.001, a batch size of 64. The results, I had the best training accuracy was 99.58%. Lowest training loss was 0.3. The best validation accuracy was 89.69%. And the lowest validation loss was 0.26. Okay. Now, the best variance was 9.9%. And it's not that good. You can see that there's a variance in here between the training and validation accuracies overall and the losses. But this is just plotting the losses, essentially. Now, here are some images of the visualizations. You can see all of them are correct. Free and actual free, predicted free, actual free, predicted free, actual free, predicted collision, actual collision. It performed pretty well. I mean, it's in nearly 90% accuracy. So it performed pretty well just using 2,880 images as its training dataset, okay? And we move on with train the model with 30 epochs. Surprisingly, 30 epochs performed better, but you'll see that there's no particular reason for it. So the epochs were 30, the learning rate was the same, 0.001, and the batch size was 64. The training accuracy, the highest one was 99.69%. The smallest loss was 0.02. The best validation accuracy was 92.81%. And the lowest validation loss was 0.20. The best variance was 0.0687, which is 6.87%, okay? That is lower than the 50 epoch training session. Here's the difference between the epochs. You can see that here they're closer, the losses are closer. Now, the images are still the same. You can see predicted collision, predicted free, actual free. And overall, like for this visualization samples, you can see that all of them are correct, but for some cases, they're not, okay? But the model performed pretty well. In most cases, it predicts well. Now, my conclusion is that overall, There was a higher accuracy for the validation stage in 30 epochs. Additionally, the variance between the training accuracy and validation accuracy was lower for 30 epochs, and the difference between losses for training and validation was lower in the 30 epoch case. However, I attribute it to pure randomness. There is no particular significance or statistical significance to the difference in epoch length. However, I can't do much without GPUs. I can add more data to make it like more accurate and perform a better statistical analysis, but I'll do that in future work. So overall, this model worked well, but I want to take it into consideration additional changes like adding more cameras, adding more images, try different loss functions, and removing the plane as an obstacle. And my assumption for removing the plane as an obstacle is that it'll make it far easier for the system to classify collisions because it only has to classify collisions with less objects. So the idea is that the less objects there are, the better the model is going to perform. So the idea is that in future work, I'm going to add more obstacles and I'm going to remove more obstacles. So I'm going to see the difference between the models. And then we're going to take into consideration that I have to place the same obstacles in the same positions. And also what happens when I put different obstacles in different positions. There are lots of possibilities for this model. However, I think I owe the viewers the access to the Google Colab notebook. You can access it here. You can also access my Google slide presentation and the comments below. You can also access the Google Colab notebook in the comments below. However, I'm going over the model right now. Let's see this model. It's going to work well. The runtime, I'm going to use a T4 GPU just to make it quicker. I'm just going to use like 200 images for the sake of expediting the process because like, honestly, I can't elongate this video any longer, but you can see it works pretty well. Like here it's loading Pybullet. It's gonna load pretty quickly, hopefully. But overall, you can see that I have more functions. I mean, I have this show image simple function, and what it does is shows the images. And in a really simple case, I'm gonna go over more Pybullet documentation feature videos. Here's the cases in which I make the robot have examples of, let's see, a collision-free space, and here are all of the collision spaces. They're all already done. Now it's moving to the data set. Here it's loading the 200 images. That's a hefty task. Hopefully it'll take like less than a minute. See, it's loading. It's loading the images. Loading the images takes nearly as much time as training the model. So we'll see. Okay. Took less than an image, only because I chose 200 images. Okay. Now it's moving on to training, I suppose. Yeah, it's training. I only use 4 epochs for this case. Don't be surprised if the accuracy is pretty low. Like, I mean, here it predicted free when the actual was collision. Here it predicted free when the actual was collision. Like, it has a really hard time predicting an actual collision if I use a small sample number. But you can play with it. You can write comments and show me what you think about this collision detection system for Frivolous Robotics Incorporated. And that'll be it for this video. Peace out.